All right, last example problem for the day. Another Bernoulli's equation type question dealing with Bernoulli's principle. Um, I thought that for those of you still sticking with me, maybe I would share a quick joke before we go on to this one. This joke is alluding to the fact that when in physics we always make all sorts of assumptions. Like with Bernoulli's, we assume that with a large tank, the velocity in the tank is zero, and you know, a lot of times we assume there's no friction and those types of things. So this joke is about a farmer. He's a chicken farmer, and he grows chickens at his farm, obviously. And he finds one day that his chickens are all getting sick. And so he wants to try to find some way to heal them. And so he calls up three men that he knows fairly well and asks them to try to find why his chickens are getting sick. Now, the first man is a mathematician, and the mathematician goes and he looks at all the chickens and takes some measurements and writes some things down and does a whole bunch of calculations and he says, you know what, I'm sorry, I can't figure out what's wrong with your chickens. And farmer says, well, that's all right. I still got these other two guys. The second guy happens to be a biologist. So he goes up and he takes some cultures and, you know, tries to draw some blood from the chickens and does all sorts of data gathering like that. He takes it back to the lab and analyzes, and he comes back and he says, you know, I really tried, but I can't figure out what's wrong with your chickens. Chicken farmer says, oh, that's all right. I still got this one guy left. The last guy happened to be a physicist. So the physicist goes out and looks at the chickens, and he glances a little bit more, and he thinks about it, and he jots a couple of things down on the paper, and he looks a little bit more and kind of turns his head upside down to see another point of view, and then he goes back to his office for a little bit, and he comes back the next day and he says, I've got it. I've figured it out. I know what's wrong with your chickens, and I've got a solution. And the farmer says, that's wonderful. I'm so excited. What can we do? And the physicist says, well, there is one problem. The solution only works for spherical chickens in a vacuum. Yeah, deathly silence. Oh well. So much for Mr. Bywater's jokes. Let's go on to example question number 3. A boat strikes an underwater rock that punctures a hole 20 centimeters squared in an area in its hole 1.5 meters below the waterline. At what rate does the water enter the hole? All right, well, this has areas. It has a distance below the waterline, so that's going to be some pressures. So a lot of things that we've got, we're looking for a rate, all right, so probably some type of velocity. Okay, so a lot of things here that tend to point us to, okay, this is probably going to be a Bernoulli's equation. Okay, so we're going to take pressure 1 plus rho gy1 plus 1/2 density times velocity squared equals pressure 2 plus rho gy2 plus 1/2 rho v squared 2. All right. So here's our boat. This is a side view. There's the water. Here's the hole. The hole is 1.5 meters below. Now notice that that's a vertical 1.5, not along the hole. Okay, so we don't need an angle. It is the actual depth, and then we do have the size of the hole. So we need to consider two different positions. Okay, so our first position is going to be on the ocean side, right? So this is going to be number 1 on the ocean side. What are the pressures and the heights and the volumes there? Okay, the second point is going to be just on the inside of the hole as the water is passing through. All right, now remember, these pressures depend on ambient pressure and other things at the position. These right here are based off of water or other fluid that is above it pushing down, right? And then these are due to the actual velocity of the liquid at that point, the fluid at that point. All right, so at the beginning, we do have ambient pressure, okay, the outside pressure, but that's going to be the same as the outside pressure here. Okay, so our two pressures are actually going to cancel out because ambient pressure is the same on both sides. All right, then we can look at the heights, right? We can look at the heights here and we can say, all right, at point 1, I am 1.5 meters below the surface of the water, which means there are 1.5 meters of water pushing down and in every direction, obviously, this point. Okay, so we're going to have rho, which is 1,000 kilograms per meter cubed, times gravity, which is 9.81, times the height, which will be 1.5 meters. All right, and then it's going to be plus 1/2 rho v squared. Now remember, if this is the ocean or lake or whatever it is, okay, there's a very large volume here. And if there's a very large volume and it's not necessarily moving, then we're going to consider that the velocity there is 0. And so we're going to be able to take that out. Okay, it's kind of the opposite of what we did in the last problem, right? The last problem we said it started, actually that was the same. We started in a tank and then it came out. Okay, similar idea, but this time it's starting outside and going in. All right, and so that's going to be equal to rho gy. Now, of course, once it goes through the hole, there's no water pushing down it, right? The only pressure pushing down it is the ambient pressure, which we've already considered and canceled. And so that height is going to be 0. It's going to go away. And so that means that it's going to be equal to 1/2 times rho, which is 1,000, times the final velocity squared. All right, so we should be able to solve for that. So 1,000 times 9.81 times 1.5, and then we'll divide by the 1/2, divide by 1,000, and then we will square root it, and we get 5.43. So 5.43 meters per second. All right, now once we have 5.43 meters per second, we can now find the rate at which water enters the hole. Okay, so usually when we have rate, we want it to be the mass flow rate. Okay, so mass flow rate is going to be the density times the area times the volume. Remember, the area times the volume is going to be given to you, but that's the volumetric flow rate. So we want to make sure that we include the density as well. So that's going to be 1,000 liters per meter cubed, or sorry, kilograms per meter cubed, times the area which was given to us. That's 20 centimeters squared. Now 20 centimeters squared is going to be 0.002 meters squared, right? Because to go to meters, we're going to move the decimal twice, and then to go to meters squared, we're going to have to move twice more. Or you can get a conversion that goes straight from centimeters to squared to meters squared, okay? It's 10,000 divided by 10,000. So 0.002 meters squared times velocity, which is 5.4. And so that will then give us 1,000 times 0.002 times the answer, which is 10.8, and that's meters cubed per second. All right, and so that's fine. If we want to put it in liters, then we would multiply by 1,000, so that would be 10,800 liters per second. That's a heck of a lot of water coming in. All right, well, that is the end. So I hope that that is helpful and that you will now be able to work your homework. Good luck.